Hello everyone, welcome to the class. Today we will learn how to design analog filters. We will go deep into the design of Butterworth filters today. Let's start. Now, an analog filter involves, it's a very important approach to the design of digital filters actually. First, what we will do is, what's the strategy that we will follow? The strategy will be to understand the design of filters in the analog domain. And then we will use the transformations to convert the design of analog filters that we have studied into digital filters. We will use transformations. We will not directly design digital filters. The strategy is that we will learn how to design analog filters. We will use that transfer function and we will apply transformations on that transfer function to design digital filters. A very important approach to the design of digital filters is to apply a transformation to an existing analog filter. The commonly required types of frequency filter fall into four groups: low pass filter, high pass filter, band pass filter, and band stop filter. Now, the first diagram shows the characteristics of the frequency response of the low pass filter, meaning by that low frequencies will be passed through the filter and high frequencies will be blocked by this type of filter. In the high pass filter, the high frequencies will be passed, whereas the low frequencies will be blocked. In the band pass filter, a certain band of frequencies will be passed, the rest of the outside the band, the frequencies will be stopped. Band stop filter is that a particular band of frequencies is stopped, whereas the rest of the frequencies will be passed through the filter. Now, next is the ideal response of the low pass, high pass, band pass, and band stop. You will see that in the ideal case there is a very almost a vertical line is there, right? So this is the ideal. Now, when you design a filter, the filter designed must go closer. Let's take the case of a low pass filter. The low pass filter design must go as close as possible to the ideal low pass filter. Now you will see that there is a roll off. It is not a sharp dip from the pass band to the stop band. So it takes a roll off and then it goes to the stop band. But in the case of ideal, so after the pass band, immediately you will get the stop band. So that meaning by this frequency will be up till here the pass band is there. Beyond this is the stop band. So immediately you will get the stop band. Similarly, the case for high pass filter. There is a vertical line. There is a vertical roll off from the pass band to the stop band. This is difficult to achieve. There are many types of filters which exist which go close to these types of responses, but it takes very high complexity. The order of the filter is required is very large to get the response very close to these types of filters. All right. Now, the analog filter design procedure normally begins with a specification of the frequency response for the filter. We will first specify the frequency response of the filter, right? How the filter will behave, meaning by how it reacts to the sinusoidal inputs. Now, if the input sinusoid is not attenuated or attenuated less than a specific tolerance as it goes through the system, it is said to be in a pass band of the filter, meaning by the sinusoid is not attenuated, or if it is attenuated, it is less than the specified tolerance level. That we call as the pass band. Whereas if it is attenuated more than a specified value, it is said to be stopped and within the stop band of the filter. For example, if you look at the diagram, this frequency, this smaller frequency falls in the passband, whereas the high frequency is stopped and falls in the stop band. This is the kind of low pass filter explanation given in the diagram. Now, this diagram shows the key filter parameters. This is the ripple involved. This up to here is the you see, this is the passband of the filter. This is the case of a low pass filter. This is passband. Starting from along x-axis is the analog frequency, right? Along y-axis is the h of omega. That means the frequency response. From 0 to up to this frequency is the passband, and the signal is not completely flat. You see the ripple in the passband. This is known as passband ripple, and it is represented by A max, the amplitude. This is the amplitude level represented by A max, and this is known as passband ripple. This point is called the 3 dB point because the DC value is 1 dB here. DC value is 1 here, corresponding to 0 dB. We will look into the details further also. This will be the 3 dB point at which the amplitude is 0.707 of the DC value, which is 1 basically. So this up till here will be called as the bandwidth of the filter. Now, from here, from this point to this point is your transition band. Up till here is your transition band. This is your transition band. Transition band means the band required so that the response goes from the pass band to the stop band. This is the stop band frequency, Fs, right? After this point, because it will fall to almost 0, after this point will start the stop band, and in the stop band also there is ripple. This is known as stop band ripple. This is pass band ripple. The signal from here gets attenuated, which is 1 basically, normalized to 1. The DC gain is normalized to 1. That means it is corresponding to 0 dB. This point is minus 3 dB, and this point will be specified by the designer of the filter, which corresponds to the stop band attenuation. So this is A min is the stop band attenuation, meaning by the attenuation required in the signal. Once it is achieved, we will call that it now the signal falls into the stop band. So these are the key parameters to do the specifications of the filter response. Now, a filter response is expressed in the transfer as a transfer function. Now, a transfer function mathematically expresses the frequency domain input to output behavior of a filter. We can write a transfer function in terms of the variable s, which represents complex frequency, and we can replace s with j omega. We all know these basics when we need to calculate magnitude and phase response at a specific frequency. The standardized form of a transfer function is like a template that helps us to quickly determine the filter's defining characteristics. Mathematical manipulation of the standardized first order transfer function allows us to demonstrate that a filter's cutoff frequency is basically the minus 3 dB point, and where the phase is shifted by minus 45 degree. The stop band frequency Fs is the frequency at which the minimum attenuation in the stop band is reached, as this is our stop band frequency as explained in the diagram. The passband ripple is the variation in the passband response that we have already seen. This is the passband ripple, variation in the passband response. The minimum passband attenuation defines the minimum signal attenuation within the passband. So this is from this point to this point is our stop band attenuation. The steepness of the filter. Now, how steepness means how sharply it falls from the passband to the stop band, meaning by the width. I'm talking about the width of the transition band. All right, that's the steepness that we call as the steepness of the filter is defined as the order of the filter, because if you want to reduce the width of the transition band, you will have to have a higher order filter, which is determined also by the number of poles in the transfer function. A pole is a root of the denominator of the transfer function. Conversely, a zero is a root of the numerator of the transfer function. Now, each pole gives a minus 6 dB per octave or minus 20 dB per octave decade response, whereas each zero gives a plus 6 dB per octave or plus 20 dB per decade response. So that means there is a minus 6 dB, um, the curve will fall down after every doubling of the frequency, or there is a fall of the curve. Fall of the curve means this will come down. You introduce a pole in the transfer function, the curve will come down where by minus 6 dB per octave, which is the doubling of the frequency, or minus 20 dB per decade with 10 times the frequency. And if you introduce a zero, the curve will lift upwards. A pole corresponds to that's what is explained here. A pole corresponds to a corner frequency at which the slope of the magnitude curve decreases by 20 dB per decade. That's in the case of a pole. And a zero corresponds to a corner frequency at which the slope increases by 20 dB per decade with the lift in the curve upwards. Slight lift. It is not resonance. There will be slight lift. I mean, the transition band, transition width will increase, kind of. All right. Now the technique. This is an important note. About the strategy that we will follow for the designing of the analog filter. The technique used to design analog filters is to specify a prototype low-pass filter function. We will take first the case of a low-pass filter function, which we will call as the prototype low-pass filter. This filter is normalized to provide a cutoff frequency. Normalization means this. Please remember this. In my lectures, I am taking this capital sigma as analog frequency and cutoff frequency in the analog domain, and this small omega c is cutoff frequency of a filter in the digital domain. But at present, since we are designing analog filters, we will deal with capital omega c. Once we will come to digital filters, then we will come across with small omega. Now, a cutoff frequency is the filter function is normalized to provide a cutoff frequency at 1 radian per second. What is the meaning of 1 radian? This is the normalized frequency. The whole frequency axis, when you do the normalization of the frequency response, when you do the normalization of the filter response, what is the meaning? Its meaning is that the whole frequency axis will be divided by capital omega c. Right. So corresponding to this frequency, capital omega c divided by capital omega c will be at 1 radian per second, and every frequency on the frequency axis will be divided by omega c, that we call as the normalization. Once it is done, then apply. Then after that, once we have specified, once we have designed a prototype low pass filter function, then we will apply direct transformations to achieve the actual desired cutoff frequencies and filter type. I mean, once it is done for a low pass filter function, then what we can do is we can design another low pass filter of different cutoff frequency, or a high pass filter, or a band pass filter, or a band stop filter from the same design done as a prototype low pass filter function. Therefore, the prime consideration will be given to a low pass filter design. All right. Now let's start with the ideal brick wall low pass filter prototype, which has a unit amplitude frequency response from DC to 1 radian per second, with response dropping to 0 thereafter. What's the meaning of this statement? We start from this frequency, which is the DC, and we reach to this point. This is capital omega c basically. But since this axis is normalized, that means this point, every frequency will be divided by omega c, capital omega c. But at this point, it is omega c point, capital omega c point, but it is divided by a capital omega c, so therefore it is 1 radian per second. This is known as normalization, as I have already explained. Now it's a unit amplitude frequency response up till 1 radian per second normalized frequency, and thereafter it is 0. This may be defined in terms of the following squared magnitude transfer function. This is the frequency response, and h j omega minus, let's take the conjugate, and if you multiply these two, you will get h j omega square. And this magnitude square response is defined by a function 1 plus f omega, capital omega square. This is a polynomial function, right? So let's look at the characteristics of this polynomial. Now where f capital omega square is 0, between 0 and 1, that's what this filter says. Between 0 and 1, it has to be 1. When omega is greater than 1, this function goes to infinity. So once this function goes to infinity, the overall response will be 0. So that's the formula by which we can represent this type of filter, brick wall filter. Since f capital omega square is a polynomial in omega square, so now we have to actually find out the ways how to define and how to find out this type of polynomial. Now f omega square is limit n approaches infinity, and you can approximate to this type of response. We will not go into the details of how you have got this. Actually, this is the Butterworth assumption, approximation that he has done. That's the contribution of Butterworth actually. But let's see, since f omega it's a polynomial, now this limit must satisfy the lower condition. Lower condition means it must go to infinity. That's why the full response will become 0. Must satisfy the lower condition in equation number 2. It is not practically feasible to form a polynomial of this type because it will require an infinity order polynomial, right? So therefore approximations to this f omega squares are made. The approximation for f omega square due to Butterworth is capital omega raised to the power 2n. Butterworth, as I said, this is actually the contribution of Butterworth, that he made an approximation to this polynomial as capital omega raised to the power 2n, where n is the order of the filter. And this we can modify the equation number 1, and we will get 1 over 1 plus omega raised to the power 2n. That's how a brick wall filter will be turned into a Butterworth filter. That's the approximation done by Butterworth. This is the contribution of Butterworth. That's why this type of filter, what we will study further, these filters are known as the Butterworth filters, right? So this is the formula achieved. This is the, now in the previous case it was square, now we take the square root, so it will be 1 over 1 plus omega to the power 2n and under root, where n is a positive integer. So this is the Butterworth approximation of the frequency response of a low pass prototype filter. Now let's see how to design the low pass Butterworth filter. Now we know that how a normalized Butterworth filter of order n is defined by, so this is omega given, this is any frequency, this is a variable. This variable frequency is divided by cutoff frequency of the filter that we have chosen to design as a low pass filter. This we call as the normalization. Now this is the normalized response. All right, this is capital omega c is the cutoff frequency of the filter. Now the following properties can easily be described. This h j omega square, I'm talking about this response, is 1 for all n at corresponding to this frequency for all orders of n, and this response is 1. We know that that's the specification at 0, and at the cutoff frequency it is 1 by 2, because if you see here, now this is the cutoff frequency. it is minus 3 dB point for a low pass filter, and this point, this corresponding, the power corresponding to this frequency is half power of this DC gain, half power. That's why this point is known as the half power point. All right. Okay. Okay, we were there. So because we are talking about the square of the frequency magnitude response, so that means it is equivalent to power at omega equal to omega c at the cutoff frequency. This is equal to half, because this is the half power point. Now this function is monotonically decreasing function. The frequency response, this function is a monotonically decreasing function of omega, both in the pass band and in the stop band. It's monotonically decreasing. As n gets larger, as we take larger values of n, the magnitude response approaches ideal low pass frequency response. And fifth point is especially the characteristic of the Butterworth filter, that is maximally flat at the origin, since all order derivatives exist with respect to omega and zero at the origin. So it is maximally flat in the pass band. Meaning, its meaning is this: it maximally flat, very less ripple you will find in the Butterworth filter. It's maximally flat in the pass band. Okay. Now we know that this is the equation, right? We can expand this equation, 1 over 1 plus omega by omega c to the power 2n. We can take this term into the numerator by taking power raised to minus 1, and we can expand this term using power series expansion, and we can replace, if we make the approximation up to this point, we can replace this term with this term, 1 minus half omega over omega c to the power 2n, rather than dealing with this minus 1. All right, this is the power series expansion we can do. Now let's look at, this is the frequency response in terms of power corresponding to equivalent to power. That's because we are taking the magnitude square. Now this point is the 0 dB corresponding to, I will come to the dB curve also, but let's say this is 1, the gain is 1 here, and if you look at n equal to 1, n equal to 1 is a straight, almost a straight line. But looking at n equal to 2, you get you start getting a roll off. If you take an n equal to 100, you get a very fine roll off like this. The curve is almost behaving good in the pass band, then it is dropping down in the stop band like this, and when n is equal to infinity, it is almost an ideal filter. Now this graph actually explains the dependence of order of the filter on the response of the filter. If you take a higher order filter, the frequency response will reach as close as possible to the ideal response. The magnitude response of a Butterworth filter with various values of n. Now this is also one way of representation of the same kind of concept in the logarithmic scale. Along the y-axis is the gain. This is basically equivalent to voltage. The previous curve is equivalent to power because it is square, and here it is only the magnitude. That's why it is 20 here. Had it been square, you would have got 10 here, 10 log hj omega square. But okay, no problem. We are plotting the logarithmic on the y-axis, logarithmic value of this magnitude response, 20 log hj omega. So this is the dB scale. At this point where the gain was 1 in the previous slide, this point corresponds to 0 dB. This point corresponds to minus 3 dB. which actually is your cutoff frequency, right? And further, if you go down, you will find more attenuation. This point will be minus 20 dB, minus 40 dB, minus 60 dB. When n is equal to 1, it is minus 20 dB per, as I said in one of my slides. Okay, let me show you there. That's an important point. A pole actually it's minus 20 dB per decade. By introducing a pole, you actually increase the order by 1. So there is a minus 20 dB drop, minus 20 dB decrease in the slope of the curve per decade. So when n is equal to 1, the slope is like this, minus 20 dB per decade. When n is equal to 2, it will be further dropped by minus 20 dB. So slope is minus 40 dB. So this is the slope and so on. Filter gain plot. This curve actually explains the filter gain plot for analog Butterworth filters of various orders of n. It is convenient in many cases to look at the frequency response in decibels as 20 log Hj omega and can be drawn as straight line approximation as shown in this figure. All right. Now let's go deep into the analysis of the Butterworth filters. This is the magnitude Butterworth magnitude squared response, right? Since square is not there, so therefore under root is there. Once we square it, this is 1 plus sigma 1 plus omega 2 raised to the power 2n. Now if we have to convert this into the S domain, right? So Hj omega square is actually equal to Hs and H of minus S. Clear? This we know from the Laplace, the traditional Laplace transform theory. And let S is equal to j omega, right? Our Hj omega, we know that S is equal to j omega. Our Hj omega is 1 over 1 plus sigma, 1 plus omega to the power 2n. What we do here is that we multiply the omega term with j and we divide the omega term with j. And we know that j omega is actually S because we want to convert this Hj omega in terms of Hs. So we multiply with j and we divide it by j. So we change this expression into S and it becomes 1 over 1 plus S by j to the power 2n under root. As I said, n is the order of the filter. Now for n, which is the order of the filter, can be even or it can be odd. Now when n is even, it will take 1 plus S to the power 2n because in that case j will be, this power will give j as plus 1, and when n is odd, this j value will be minus, so it becomes minus here. So j will give either positive or negative 1 depending on the power of depending on this power, and it will depend on whether n will be even or odd. Okay, so let's take the case when your n is even. So in that case, let's take this Hs, and because this is the denominator value and this is the characteristic equation, because we want to find out the roots of this equation and hence the poles. So we will put it equal to 0. Now from this equation we get S to the power 2n is minus 1, and minus 1 we can represent as e to the power plus minus j pi. Now we can also write e to the power plus minus j pi as plus of j to pi k because it will be a repetitive function where k will be varying from 0, 1, 2 up to n minus 1. We will see the importance of k. Now, so therefore S to the power 2n is e to the power plus minus j pi 2k plus 1 by taking j common from here, and taking this power which is 2n to the other side, hence the equation becomes ultimately this. So final equation is e to the power plus minus j bracket starts pi by 2n plus k pi by n, where k varies from 0 1 to 2n minus 1, because 2 will come from up to 2n minus 1. All right. Now, when n is even, the first pole will start at pi by 2n, right? That is k equal to 0, and the remaining poles will be equally spaced around the unit circle by pi by n. That's what is the meaning of k, and k will give the number of the remaining poles which will be equally spaced. So this is n minus 1, this 2 is not there. All right. So this is how we will be able to get the position of the poles when our order of the filter is even. Now, this is how the representation are, because the locus where the poles will be placed will be a circle, and the center of the circle is the origin of the S plane, and the poles will be uh, separated from each other by pi by n, right? And this is the case. Left side of this y-axis is HS plane, HS, HS transfer function, and the right side of the j omega axis is h of minus s. All right. The system HS into h of minus s is a combination of two cascaded systems, where the poles of one system is obtained by reflecting the poles of the others. The same poles will be reflected to this side, or this side poles will be reflected to this side. Will be by reflecting the poles of the other system about the origin. That is, if S is a pole of HS, then minus S is a pole of H of minus S. Let's take this example. When n is equal to 2, in that case, k will be 0 and 1. For k, when k is 0 and 1, we will get this pole e to the power plus minus pi by 4, and these two poles will lie in the HS plane. These two poles will lie in the h of minus s plane, and these two poles will lie in the h of s plane. Because it is pi by 4, this pi by 4 pole is this one, minus pi by 4 is this one. 3 pi by 4, 3 pi by 4 is this one, and minus 3 pi by 4 is this one. So that means these two poles will lie in the HS side, and these two poles will lie in the HF minus S side. So therefore, in total, there will be 4 poles when n is equal to 2. That means n is even. All right. So from this analysis, we actually get the position of the poles. And once we get the position of the poles, we can also get the transfer function of the system when n is equal to 2. That means it is a second order system, second order transfer function. We will see that, and we will derive the transfer function also. Okay, now let's take the case when your n is odd. In that case, the minus sign will come here in the characteristic equation. So 1 minus s to the power 2n under root is equal to 0, which will give me s to the power 2n as 1. So I can represent this as e to the power plus minus j 0, because any thing raised to the power 0 will be equal to 1. And I can put it like this: e to the power plus minus j 0 plus 2 pi k, where k varies from 1 to n minus 1. In the final case, my s to the power 2n is, because this is 0, it will be e to the power plus minus j 2 pi k. And taking 2n on this side, so this 2 will cancel out, and final equation for the poles is s is equal to e to the power plus minus j pi k by n, where k varies from 1 to n minus 1. So it provides how many poles? It provides actually 2n minus 2 poles. And 2 poles are there for k equal to 0. Here k, we are not considering k equal to 0. So when k equal to 0, it will provide one pole at 1, right? Along the x-axis, when the value of the x-axis abscissa is 1, so it will provide the first pole. When it is k equal to n, the abscissa on the x-axis will give me the value as minus 1. So two real poles will be there actually, and the rest of the complex conjugate number of poles. In that case, total number of poles will become 2n minus 2 plus 2, that means 2n poles. Let's take one example to understand this. This is the general example of a when n is odd. This is one pole, the real pole. This is another pole which is also the real. So that, as I said, two poles will be real poles and rest will be complex conjugate. So complex conjugate pair of poles. This pole is a complex conjugate of this pole. This pole is a complex conjugate of this pole in the h of minus s side, and the same thing will happen in the h of s side. And the poles are equally spaced on the unit circle by pi by n in angle. All right. Now let's take the example with n equal to 3. The poles of the Butterworth filter all lie in the left hand side of the S-plane with a locus which is a circle of unit radius whose center is in the S-plane origin, as I have already explained. Now when n is equal to 3, what will be when n equal to 3? So these will be my poles. Right, from here I will get my poles. These two poles are there, of course. One is at abscissa 1, which is this pole and this pole, and two other poles will be there. One is let's look at this. It is pi by this is pi by 3, right? This is plus minus pi. Sorry, this is the equation where n will vary from n is 3. K will vary from 1 to 1 to 2, right? So you will get because plus minus sign is there. You will get 4 more poles. 2 poles are these, and 4 more poles from here. So that means in that case you will get total number of 6 poles. The pole position on the h of minus s side is 60 degree, and pole position on the h of s side is minus 60 degree, and this is coming from the same formula which we have derived. So total number of poles will be 6 poles when our n is equal to 3, and all poles lie on the locus, which is a circle of radius 1, and the center of the circle is the origin of the S-plane. All right. And this is the case when n is equal to 4. Another case when n is equal to 4. And this is how the pole positions. These things are coming from the same formula. So you will, depending on the order of the filter, Butterworth filter, you will have the pole locations which you can obtain from the analysis or the derivation that we have already done. In both the cases, when n is even or when n is odd. All right. Now let's take one example. We have to actually find the transfer function Hs for the normalized Butterworth filter of order 2. Order 2 means when n is equal to 2. Normalized means omega c, capital omega c is equal to 1 radian per second. Now when n is equal to 2, we know we have already derived this formula. We know that s is equal to plus minus j pi by 4 plus k by 2. So k will vary from 0 to 1. When k is equal to 0, these two poles we will get. When k is equal to 1, these two poles will get. Okay, these two poles will lie in the h of s side, and these two poles will lie on the h of minus s side. When we are asked to find out h of s, that means we have to use these two poles. That's what is done here. We will use this pole and this pole because we have to find out the transfer function in terms of h of s. So when we know that there are two poles, we can represent h of s as 1 over s minus s1. This is the first pole. And the second pole is s of minus s. So this is how we can represent the transfer function if two poles are there in the left side of the S-plane, right? And the position of these poles we know because this angle is minus pi by 4. So we know that it is minus 1 by under root 2 along the negative this sigma axis, you will have minus 1 by under root 2 and plus 1 by under root 2, right, on the above the x-axis. This is first pole. The second pole is this pole. From where this minus 1 over under root 2 plus j 1 over under root 2 is coming? This is coming from this value, e to the power plus minus j 3 pi by 4. We can put it as cos of 3 pi by 4 plus minus sine of plus minus j sine of 3 pi by 4. So this 1 by under root 2 is plus j 1 by under root 2, and the second one is coming from using the Euler's formula, where e to the power theta is equal to cos theta plus j sine theta. All right, and so we get the transfer function which is hs like this. Now if you solve it further, open the brackets and multiply the two values in the brackets. So you will finally get h of s is equal to 1 over s square plus under root 2 s plus 1. Now this is a normalized transfer function we have got. From where we have come to know that this is normalized, you will always get 1 here in the case when the transfer function is normalized. Normalized implies omega c is equal to 1. So you will get 1 here always in the transfer function. If we say that now this is a normalized transfer function, why? Because 1 is here. There is a procedure to denormalize the transfer function also. In that case, you will have to replace you will have to replace this s by s of s divided by omega c. We will see that part in the next examples. So this is the transfer function we have obtained when the value of n is 2. That means the order of the filter is 2. We can know from the transfer function also that the order of the filter is 2, because the highest power of s is 2 here. Therefore, it is a second order filter transfer function. Right. Now let's do one more example. Determine the transfer function of a Butterworth filter of the low pass type with order n equal to 3. Assume that the 3 dB cutoff frequency is in radian per second, is 1 radian per second. So that means it is again normalized. We know that when n is equal to 3, the total number of poles will be 6, and we also know the equations from where we will come to know these are the equations which we will use. This is the these are the one set of poles, and these two poles will always exist. From here we can get the position of the poles S1 as on the HS side. Definitely there will be a pole on the HF minus S side also, but since we are asked to determine h of s, so we will take S1 as minus 1, S2 and S3. So these three poles will be there, and we will use 1 over S minus S1 into S minus S2 into S minus S3, and we will use these pole values, and we will substitute the values, we will multiply inside, and we finally get this 1 over s cube plus 2s square plus 2s plus 1. This is the transfer function of a third order Butterworth filter. The transfer function of a Butterworth filter of order 3 is therefore this. So that means we can find out the transfer function of any order Butterworth filter. We will not calculate the order, we will not go for the solution of transfer functions for other n values, but we will make a table where we will be able to get the Butterworth polynomial. What is the Butterworth polynomial? It's the denominator side of the transfer function. On the numerator side, it will always be 1, because it's an all pole filter. Butterworth filter is an all pole filter. So when n is equal to 1, it is s plus 1. We have already derived it. When n is equal to 2, it is s square plus under root 2 s plus 1, already derived. N is equal to 3. This is the Butterworth polynomial. So 1 over this polynomial will give me the transfer function directly. We can use this table also. Similarly, for order 4 and order 5, we have the Butterworth polynomials. The procedure remains the same for the calculation of the transfer functions and finally the Butterworth polynomials. Okay. Now let us design uh, a Butterworth low pass Butterworth filter. This is an important question in which we have to design an analog Butterworth filter that has -2 dB or better cutoff frequency of 20 radian per second, right? And at least 10 dB of attenuation at 30 radian per second. So this is now this frequency of 20 radian per second is not at -3 dB. That means it is not the cutoff frequency. This frequency is some other frequency at -2 dB attenuation. If we draw the characteristics along the y-axis, it is 20 log h of j omega or 10 log h of j omega square, because this represents power, this represents voltage. So this -2 dB attenuation at this point, right, from where the curve starts, it is 0 dB, right? And you move down at -2 dB, it says the frequency corresponds to 20 radian per second. It's not 3 dB, -3 dB frequency. That means it is not the cutoff frequency. It is omega x. That's why I have written here omega x. I have not written omega c, which is actually -3 dB frequency. And at least 10 dB of attenuation at 30 radian per second. So that means you go further down at -10 dB attenuation, because this is attenuation, that's why we are taking minus sign here. -10 dB attenuation, the corresponding frequency is omega s, which is 30 radian per second. These are the specifications given, and we are to design an analog Butterworth filter. Now, what is the meaning of designing an analog Butterworth filter when these specifications like this are given? In that case, you will have to achieve these specifications, you will have to find out first the order of the filter, second the transfer function of the filter, and the cutoff frequency also. So three things you have to find out. First, small n, which is the order of the filter, second the transfer function, third the cutoff frequency. Let's try to solve this question. We know that this is the Butterworth equation, standard Butterworth magnitude squared equation, right? Now we will use the power type of relation, which is 10 log hj omega square. We take the log on both sides and multiply it by 10. So this will be my result. Now I will use two values, k1 and k2. So that means k1 is -2 dB and k2 is -10 dB. Rather than straightway putting these values, I will use the general variable here, which is k1 and k2, general constants for this example at least. We can use for the others also. So k1 is -2 dB, actually k2 is -10 dB. I will use here k1 at omega x. We know that k1 is at omega x, k2 is -10 dB, which is at omega s. So one is at x, the other is at s. Let's try to look at this side. Let's say this is k1, because this thing is 10 log hj omega square. So we are given that it is -2 dB. So that means the whole value is -2 actually. That means it is k1. So k1 is equal to 10 log 1 over 1 plus, and we will replace this omega by omega s x, because this k1 is corresponding to omega x, right? We solve it further. We will take this 10 on this side. We will open this logarithmic. So log 1 minus log of this value, log 1 is 0. So we are left with, because this minus sign will go to this side, minus k1 over 10 and log of this expression. Now take, because this is log to the base 10, so take log on the left hand side. So this part, which is 1 plus sigma x over 1 plus omega x divided by omega c to the power 2n is 10 to the power minus k1 by 10, right? And we can further find out omega x by omega c as 10 to the power this value, 10 to the power 10 minus k1 by 10 minus 1. And equivalently, we can say k2 is equal to this, because this is minus 10 dB, so we can say k2 is equal to this. But in this case, this omega will be omega s. In this case, it will be omega x, right? So omega s divided by omega c, as we have reached to this expression for k1, similarly we will reach to this expression for k2. So we have two expressions, one for k1 and k2. We divide these two expressions, we get this value, right? And you see here omega c is common in both sides. Omega c will cancel out, and we are left with this, because this is 10 to the power minus uh, now this will be omega x by omega s. We will take log on both sides. Once we take log on both sides, this 2n, which is raised to the power, can come out from here. So 2n can come out from here, and this will be log to the base 10 and this expression. Now if you solve it further, you can find out the value of n from here, because you know omega x also, which is 20 radian per second, omega s also 30 radian per second, minus k1 also, which is minus 2 dB, sorry, k1 also, which is minus 2 dB, k2 also, which is minus 10 dB. So all those values are put, and we can calculate the value of n from here. Now my n comes out to be 3.3709. We cannot derive the transfer function or the Butterworth polynomial for this fractional value. We will take the next higher integer, so which is 4, and we will take the Butterworth polynomial from the table corresponding to fourth order filter. All right, so that means we can derive. So if you remember the table, this is the table, and corresponding to fourth order filter, this is my Butterworth polynomial. What will be the transfer function? 1 over this Butterworth polynomial will be my transfer function for this filter design for these specifications. All right, this is how the calculations are done. This is how the design part is completed. Now we need to calculate the cutoff frequency also. We take one expression for K1. We can take K2 also, but we take for K1, right? Now we further manipulate this expression and extract omega c out. Therefore, omega c is this value, omega x by 10 to the power minus k1 by 10 minus 1 raised to the power 1 over 2n. So all values we have, this is 20 dB, this is minus 2 dB, n is 4, because we have already assessed that the order of the filter required in this case is 4. And this is my cutoff frequency coming, which is 21.3868 radians per second. And finally, this is my normalized low pass Butterworth filter for omega c equal to 1, because for n equal to 1, this is my Butterworth polynomial. For n equal to 4, this is my Butterworth polynomial. This is normalized low pass filter transfer function. I have already calculated omega c, which is 21.38, right? So if I have to denormalize this transfer function, you have to replace s by s over omega c. Omega c I have already calculated. So if you replace everywhere in the normalized transfer function, this is the procedure. Everywhere in the transfer function for Hs, if you want to get a denormalized transfer function, you replace s by s over omega c. Replace everywhere s by omega c. You have to get the expression in terms of s. Omega c value you know. So this is my final expression of the transfer function, which is a denormalized transfer function. Now you see it is not one here. If it is not one here, that means it is denormalized. But it is one here and here also. So therefore, it is normalized transfer function. Whenever you will have one here at the last position, that will be a normalized transfer function. And whenever you denormalized it using this procedure, you will not get one here, and it will be in the denormalized form. All right, so that finishes the design of the Butterworth filters. Next time we will see some transformations. We will also deal with Chebyshev filters and also the design of digital filters. Thank you. N, which is the order of the filter. Now